MIT Arrow Georgia Tech, who is going to discuss efficient learning with smooth data.
Oh, I'm ready whenever.
You can start. Yeah.
Okay. Yeah, thanks again for the invitation and thanks for sticking around for the last talk. Hopefully, I'll entertain you for the next 45 minutes and then you can go enjoy it rest. So, so I'm going to talk about efficient learning with smooth data, and this is slightly different from other talks we've seen in the session. So I'll think about a bit more about like statistical learning, foundations of statistical learning, and sequential decision making. So it's in a slightly more abstract setting. So feel free to ask any questions. Stop me if anything is not clear. I don't have to cover all my slides. So okay, so stop me for questions. So the key takeaway that's if again you learn nothing from the talk, the main thing to understand is this notion of smooth data, which I'll introduce, will be a framework in which you can bridge the efficiency of statistical learning with the robustness of online learning. So that's sort of the um, approach that we want to talk about. So that we're all on the same page. I'm sure everyone here has seen this already, but to make sure that we're on the same page about notation, I'll talk about statistical learning to begin with. So in the setup of statistical learning, you have t data points that t will be the number that sort of I'll think about as the number of data points which come from some distribution mu, and you'll have y hat which is labeled from some function f, and maybe you have some noise. So again, we'll think about noise as being mean zeros, not super important right now. Further, you'll have access to a class of functions which I call the model class, which is a set of maps from x to y. Think of x as maybe rd and y as like r or something like that, but again it will be in some abstract setting. And again, be more concrete, you should think of the model class as a set of neural networks or a set of decision trees or something like that, like a set of classes that you might be interested in, but everything I say will be in this abstract setting. Okay, so the goal of statistical learning is to return a function f hat that has small test laws. Again, I'm reparameterizing test laws in a slightly strange way. You'll see why a bit later. But you sample t different points from the same distribution and ask how many times you make a mistake in expectation over the sampling and also on the training data. Okay, so and think of the loss function as either the square loss or the classification loss. Again, not much of what I say will like be super dependent on the loss, but again, whatever is easiest to think about. And when I have prime variables, I typically mean that they're like resampled from the same distribution as the unprimed variables, but independently. Okay, so the questions that we are interested in are firstly the algorithmic question: what is the algorithm that you should be running if you want to get good performance? And what sort of computation should you be running? Like, what is the algorithmic techniques that you should be using? And the more sort of fundamental question is how much data do you need to get good guarantees? And secondly, what makes a problem hard? So, what part of the setup allows you to be able to learn at all? So, what function classes are learnable? What data distributions are learnable, and so on? These are again the types of questions that I want to think about. So, the algorithmic question itself, at least in statistical learning, if you don't care about running time, this is sort of well understood. The general framework to think about how to design algorithms for this is something called empirical risk minimization. It's just a fancy way of saying take the data that you have already seen, fit the best model in the class that you're thinking about, and just output the function that minimizes this loss. And for this algorithm itself, we have a good understanding of how much data we need and what makes this problem hard. So for the performance of VRM, very classical results tell you that as long as the function is somewhat Lipschitz or has appropriate Lipschitz proxies, and if f hat is ERM, then the expected error is upper bounded by something called the Gaussian complexity of the function class, which happens to be upper bounded by the VC dimension. Again, if you don't know what the VC dimension is, it's not super important. Think of that as some small number as a function of, maybe I shouldn't say this in a neural networks conference, but for now, think of that as a small number and relative to everything else, as relative to other things we'll see. So the Gaussian complexity is just how well your function class can fit random data. That's uh, and again, the VC dimension happens to be the size of the largest sharded set by the class. Again, some notion of complexity of the function class. So this is supposed to be a small number, and we can talk about if this is indeed small, maybe offline. Okay, so another interesting thing happens when you have the square laws instead of say, an abstract Lipschitz laws. You tend to get a faster rate instead of getting this 1 over square root t rate. You get this faster 1 over t rates if you run ERM. This happens because the square laws has curvature. And just as again, just to compare the two bounds, you get this fast rate here, and the slower rate if you have a sort of general Lipschitz loss function. This will come up a bit later why this difference matters. Okay, so again, TLDR about like what statistical learning is, what you can expect to be able to do. So this is entirely is fully understood. The key modeling assumption that statistical learning is sort of based on is that the data that you get from at train time is independent of each other and also independent of the test point that you are evaluating your risk on. So somehow you this assumption is sort of the key modeling assumption that you are running that is behind all statistical learning theory. So the key question that we want to talk about in today's talk is this assumption too strong, and is this like when can you relax this assumption? What under what assumptions can you actually get sort of bounds that are comparable to what you can get under this? Again, what I'm calling a strong assumption, and there's sort of good reason to think about this. There are many problems that we might be interested in are fundamentally sequential. For example, like uh, problems that come up in like serving ads and recommend assistance, everything something that everyone's interested in now, which is like say language models and like chatbots. Is fundamentally sequential in how how they address problems. And there are various other examples, maybe robotics, where like and reinforcement learning, where it is not reasonable to sort of think about your points xi as independent. So that's it's actually funny. It gets funnier, but I don't have time to. Uh, so anyway, so the point I guess I'm making is that the assumption of independence, though it's a good place to start, it in many applications it is not. It happens to be too strong and does not capture the interesting behavior in the data. And further, like um, at sort of a more fundamental question about how to model the real world, one can ask where does independence even come from? Why is the independence assumption sort of well founded? And maybe some part of this work will try to address what do you need from independence to be able to say intelligent things about statistical learning. So that's also part of the goal of this line of work. Okay, so one solution to this problem of like assumption of independence on your data is this other model called online learning. And many of you might have seen versions of this under the name of experts or like multiplicative weights or some other name like this. But this is again an abstraction of algorithmic problems of that sort. Here the setup is again very simple. You get t data points, they're just generated arbitrarily. There are no assumptions on anything. And you again have a model class, which are a set of functions from x to y. And now what you want to minimize is this notion called regret, which is just the number of mistakes or the loss that your algorithm suffers on the realized sequence compared to the loss that the best model in class would have suffered if it was given the entire data set to train on. So this amortized over time. So this quantity is called the regret. Any questions on what it is? Just to be clear, there's no assumption on anything on the data itself. So only assumptions happening is I'm comparing to this benchmark. Okay. So the reason why this is interesting, even though it might seem very stylized, is that a bunch of I mean recent and like sort of classical work has reduced very sophisticated sequential decision making problems such as reinforcement learning, bandits, and things like that to essentially this task. And somehow this happens to be sort of the prototypical algorithmic primitive or based on which you can like solve like many sort of sequential decision making problems. Happens to be really important in like algorithm design, games, and so on. So it's a very sort of fundamental object to think about. Okay, so again, you can ask the same sort of question, which is, what algorithm should you be using, and you can ask how much data do you need, what makes the problem hard. So the questions all sort of remain even in this abstract setting. So this also happens to be understood, and now you replace this thing called what I called the Gaussian complexity before with this thing called the sequential Gaussian complexity, and what I call the VC dimension with the Littlestone dimension. And okay, so if you're not convinced that the VC dimension is small, the Littlestone dimension always happens to be larger than the VC dimension, and furthermore, basically, for any function class of functions that you can think about, the Littlestone dimension happens to be infinite. And maybe this is not super surprising because if you make no assumptions on the data and no assumptions on the label, you should not be able to learn too much. But you can sort of mathematically formalize this in terms of the Littlestone dimension. Okay, so furthermore, online learning also happens to be computationally hard, even in settings where you can do optimization. That is, if I somehow magically tell you that there is an oracle that solves appropriate optimization problems with respect to the class, you still can't solve the online learning problem, even if it was statistically possible. So somehow this like somewhat harder task is fundamentally harder than the corresponding statistical learning problem. And okay, so here's a quick explanation of why this is hard. It's not super difficult to see. As again, so sorry, the example will come in a few seconds, but like at a high level, what statistical learning gave you is some intuitive notion of learning. It sort of captures what we think about as learning. And again, a magical thing, at least in my opinion, is that in statistical learning, learning reduces to optimization. So the only thing you need to do is go collect data and run an optimization algorithm, and you get this again guarantee of learning on unseen data. So somehow generalization happens, at least if you are willing to make the assumptions on the data that I said earlier. But again, the issue is that it's a very strong modeling assumption, and furthermore, it's not robust at all to uh, outliers and things like that, at least naively. Online learning, on the other hand, is extremely robust. So you make no assumptions on the data generating process, and it models robustness in a completely arbitrary way. So it captures essentially like every notion of robustness that you would have liked to have had because it's arbitrary data generating processes. But unfortunately, you get, again, because it's such a strong assumption, you get statistical hardness. And furthermore, you also get computational hardness. At least one way to think about it is that you can't just go out, collect data, and just use an optimization algorithm, at least in a simple black box way, to be able to get guarantees in this setting. So learning is just genuinely harder than optimization, at least in some formalization of that sentence. So this is a high level challenge, and what this motivates is to try to find something in between the two extreme ends, where you capture maybe some notion of robustness that online learning tends to give you, and still have the guarantees and like this at least again this interesting phenomena where you can use optimization algorithms to get learning guarantees that statistical learning tends to give. So the key question you want to answer is there anything in between that somehow meaningfully captures the goodness of both extreme ends? And the what I want to hopefully convey in today's talk is this thing called smooth data, which is line of work I've been involved in for the past few years, and just try to answer this question at least. I think affirmatively. Okay, so what's the model? Okay, any questions about the motivation from, I think now on, it's mostly like math. Okay, that's good. So let's do math. So what's the model that we're interested in? The setup is it's called smooth data for the reasons you'll see in a minute. But for two measures, P and Q, so P and mu, the P is said to be sigma smooth with respect to mu if the Radon-Nikodym derivative, likelihood ratio, is uniformly bounded by a number that I'm calling 1 over sigma. So it's not super important the norm itself, but like just think of this as like some bounded likelihood type condition. You can relax this significantly if that was what you're interested in, but this somehow captures most of the interesting phenomena. Okay, so the original motivation for this was from the smooth analysis of algorithms, which is again a successful full way of thinking about interpolating between worst case and average case in the analysis of algorithms. This goes back to the analysis simplex by Spielman and Teng, but there are like predecessors of this and successors of this line of work. And this, the motivation is somehow it forces data to be anti-concentrated in ways we'll see in the future in the rest of the talk. And okay, so for intuition, just think of mu as some uniform distribution on some discrete set, or think of like something like mu is the Lebesgue measure on RD, and the distribution that you're seeing is like some point X plus some noise added to it. Like, so to connect it back to smooth analysis, if that's something you've seen already. Okay, so online learning in pictures now is the setup where the what I'm calling the adversary, the data generating process, is giving you sort of arbitrary points in some space X. So they can do sort of somewhat arbitrary things in each time, give you some completely different point that you have not seen before. And this can go on for a little bit. And the smooth online learning setup is exactly the same as before, where instead of seeing arbitrary points xt, you see xt coming from a smooth distribution with respect to some measure mu. Right, and the rest of the setup is exactly the same, and I guess the expectations include all the expectations and all the randomness that's happening. Okay, so this is the setup of smooth online learning. Is there any question about the setup? Yes.
You are saying this what the theory they measure based on. Are you trying to
So somehow it's all hidden in the complexity of f. But for now, think of it as RD or something like that, and I want to be like sort of efficient in D, if that helps. But like in this abstract setup, somehow that doesn't matter. It goes into the what you'll see as a complexity term or in terms of f. If that makes sense, but I can think of it as RD. If that helps. So that's true and also not true, because somehow, at least in this abstract setting, the adversary has enough power in one dimension that somehow increasing dimension doesn't help in the fully adversarial setting. But in the statistical setting, it does, and that's what we'll reduce to. So in that sense, yeah. Okay. But it's a good question. Again, maybe ask me again in a few minutes. Yeah. Any other question? Good question though. Okay, so now the process is the following. Instead of having points that come arbitrarily, you have, oh yes. Yes, so turns out it will not matter at all in some sense, but this is maybe not that surprising, because in like statistical learning also you basically had no constraints on mu to get like a good rate. So again, basically had no constraints on mu. At least again at the scale that we're talking about, but somehow like whatever you can get in the statistical learning, that's what you'll get in this setting as well. So yeah, but yes, short answer is basically no. Any other question? Okay, so somehow the setup is, again, think of mu as a uniform distribution on some set, this like nice yellow looking set, and smoothness is sort of saying that you have some distribution that's supported on some like somewhat non-trivial fraction of the domain, and then you sample a point, and then depending on this point, you can the data generating process can pick another distribution that can again depend on that point, and then sample one more point and repeat this, and this can go on for a little bit. So this is sort of the generative process that we are trying to learn with respect to. Right? Again, in the statistical learning case, you got samples from the same distribution. In the online learning case, you got some more arbitrary points. In the smooth online learning case, you get measures, then you get samples from them, and then looking at that, the generative process can give you pick another measure which you can sample from. Yeah. Cool. So I'll quickly talk about like what again the sort of distinguishes the this from like physical learning and online learning, like, or maybe the example will help the class to think about is linear thresholds. Again, even in one dimension, it's sort of fine. Just so that we're all on the same page is the setup. And what makes online learning hard somehow is that, let's say so far this is the data you have seen. So the red points is negatively classified, the blue points are positively classified. So in between there's like a region where you just have no idea what the labels can be, and somehow an arbitrary process can focus points there. So there's not much you can do. So you'll make a mistake each time. So somehow that's what's happening. Why is smoothness helpful? Again, at an intuitive level, the high level idea is that like if the gray region has some width of epsilon, somehow the probability that a new point with respect to a smooth distribution can fall into that gap is sort of becomes smaller and smaller as epsilon becomes smaller. This intuition sort of makes sense to think about. The real challenge is, again, I wanted to say this for arbitrary measures, not just like the Lebesgue measure or like width and things like that are like in somewhat abstract settings. But this is the intuition to sort of keep in mind. It does not somehow, yeah. So that's part of the yeah. Again, with the example, it's not maybe clear why that's true, but it's a super abstract. Like you can pick an arbitrary measure and the likelihood ratio to be bounded with respect to that, and that measure could be a delta mass, for example, and that's totally fine. But maybe we can talk about it offline. But yes, it's just, it does not depend on the smoothing process at all. So again, the hope is to get to understand how smooth analysis lies in between. Okay, so just to be all on the same page, I'll consider a super simple setting to convey that like there's something non-trivial is happening in, here. So I'll consider the well-specified sort of regression setting. So think of L as x square loss or something like that. And the YT is, I mean, again, I want to handle arbitrary labels, but for now, just think of it as it comes from some function in the class, and you're getting that function plus noise. I'll even ignore the noise in 1 second, but so this is the well-specified setting. Again, you have a function class, and you want to try to get like low error. So the your number of mistakes or whatever, so is small on average. That's what you want to get. So there's no like comparator because that's like 0. That's all I guess I'm saying. So it's just a simplified setting, so it's easier to keep track of. And also you can ask this question whether mu is known to the learner or not, or what inductive bias you have on mu. So for this talk, it won't that won't even matter. So think of mu as not known. It's just some counterfactual object that just exists. You don't have any access to. At least the learner has no access to it. Okay. And I'll also ignore the noise part. So for now, again for this talk, but everything goes through with noise too. Okay, so what's an algorithm you can try to do? You can just try to ask if empirical risk minimization online, as in you just fit the data that you have seen sequentially, whether this works. So again, as before, you see your data, and at each time step, what you do is you just pick your function as a minimizer of the loss on the data you've seen so far. Right? This is an actual algorithm to want to run. And you can ask how this algorithm does when you have data from the smooth process. And again, the goal is to get like small error. Cool. Okay, so the result that I'm going to talk about in for the rest of my time is this result with Adam Block, Sasha Rockton, and myself, that when you have a sigma smooth process with respect to some measure mu, like an arbitrary measure mu, and ft is ERM, then the error, the amortized error, is bounded by the VC dimension times log t times 1 over sigma. Okay, again, the log maybe doesn't matter, divided by sigma over t. So it's you get some rate that just depends on the VC dimension of the class and not the relational dimension or something more complicated than that. In particular, you can learn like linear threshold. Okay. So this is to be compared to when you have IID data, you basically get the same rate, but it's like a slower dependence on the slower scaling on time. You get like VC over T. So that's what you would get if you had just IID data. And we'll talk about comparing to this in a second. Which one? So for square loss, I guess you don't have a square. Yeah, you don't have a square root. And if it's realizable, also in classification as well, you don't have a square root. Somehow, yeah, this is where maybe things get interesting. And you can ask whether we were like, so comparing these two bounds. You can ask whether we were just bad at analyzing things. So let's set sigma to be a constant, then these two numbers are still not equal, right? So, but we sort of show fundamentally there's a lower bound. That is, if you have an unknown, if your mu is not known, again, just think of it as some abstract measure, the rate is actually fundamentally slower. So you fundamentally have to pay for sort of like covariate shifts. D is not the ambient dimension, it's the VC dimension of the class. Again, so think of this as like some abstract notion of dimension, but again, if it has linear classifiers and D dimensions, those two things are the same. So to learn linear classifiers in D dimension, you need a slower rate. So for square loss, you would have gotten D over T, and now you get square root D over T. So somehow again, you have to pay for covariate shifts. It's a fundamental gap. So it's not, yes. So he fixes mu, and then at each time step he's picking PT subject to the smooth constraint. Yes, yeah. And I mean FT can be adaptively picked as well, but let's again ignore that as fun. Any other question? That's a good question. Okay, so again in smooth online learning you get this like VC dimension over sigma over square root T, and somehow this tells you that like smooth data maybe in some sense, at least qualitatively, is closer to statistical learning, but quantitatively at least it's harder than statistical learning, because the rate you get is fundamentally slower, even for sort of constant choices of sigma. Again, just to clarify, if sigma was 1, this is like IID data, right? Because you're picking the same measure again and again, because the likelihood ratio is bounded by 1 and only measure that satisfies this. Does that make sense? And at least in some quantitative sense, somehow it is closer to online learning, at least farther away from this. So any questions about the setup? Again, the next few slides will be some technical stuff. Yeah. Yeah, exactly. Because if I any measure that satisfies this has to be, I mean, this is some if dp by d mu is like is 1 t equals mu. I'm saying it's not deep, it's just
E P C B D A B C B D B.
So if sigma is 1, it is basically like IID. But like if sigma is like 1 over sigma is 2, it's not like IID. That's I guess the point I'm making. Somehow like you think of like the sigma is like, if you just think of it as likelihood ratios and somehow like you're just paying for like scaling or something, that's not what's happening, is the point I guess I'm making. Yes. Yeah, so good point. You're paying a lot of attention, I guess. So sigma has to be less than a half or something like that for the lower bound to be lesser than 1 minus 1 over square. Like, so it has to be bounded away from 1 somehow for the lower bound to happen. But yeah, that's a good point. Yes. So it's a little annoying to get that. I mean, I guess like for like sigma has to get like extremely close to 1 to for like that thing to dominate. So I don't see why like you would like be interested in that regime. What I mean is that like even if sigma is like 0.99, you still get this lower bound. For any constant sigma, you still get this sort of like this term would dominate, the square root term would dominate. So you have to be like 1 minus something that goes on with t for like for the regime where like that would hit in, which is interesting maybe, but that's like already like that's like that is no distribution shift somehow. Yeah, like any distribution shift you have to pay. That's I guess the point I'm making. Yeah. Any other question? All good questions. Okay, so that's I guess the point I was making, and now I guess we'll try to understand why this is interesting and what's happening sort of at a technical level. So when you're trying to do ERM with realizable ID data, you sort of need two facts about your IID-ness, which becomes key. The first fact is that the loss on the history is sort of an unbiased estimator of the loss on the future, which is the because it's the same distribution. So the loss of any given function tracks the loss of the any of the same function on future data points. This is a very useful fact. And the second thing is some notion of concentration, which is that so there's like a standard empirical process kind of argument, which is the for any even data dependent choice of function in the class, the loss of that function compared to, so ignore the 2 for 1 second, that's some special thing about the square loss. The loss of that function compared to the population loss somehow is bounded by some complexity measure on the function class divided by t on average. So this is like an empirical process kind of guarantee. Um, if you've seen any analysis of statistical learning, you'd have seen some version of this. VC dimension, Rademacher complexity, all of those too. Some version of this. For the square loss, you need this offset too, but that's some technical thing. You can ignore that if you haven't seen that before. Oh yeah, exactly. So any hat, any prime thing is an independent copy somehow. So some population version of this quantity is like tracks the because G you have to pick in a data dependent way. So that's where the soup is coming from. So that's the sort of typical analysis. There's some localized version of the typical analysis for this. And yeah, so the complexity term somehow is like captures how rich the class is, how much it can fit noise and so on. And the class that you'd apply this to is somehow just the difference between the function and its like square, the ground truth or something like that. That's why G versus like F, but it's again some technical thing, we can ignore that for now. Right? Okay. So yeah, quickly going through the analysis, because again these two things track each other. You can replace F by the ERM, and then because the ERM only suffers sort of lesser loss on the data than the ground truth, you can just remove that term because that's going to be negative, and then you're going to get a regret point. So this is sort of like on a high level how statistical learning is done in like 1 minute. So yeah, okay. So this is the analysis. Now, the key facts that you use, again, just to reiterate, is that the data was for any fixed function is an unbiased estimator, and you had some control on some empirical process type quantity, where like the population risk, at least for data dependent functions, you can sort of control them in terms of their expectations on the distribution. So that's like sort of like what's happening in whenever you analyze statistical learning. So now you can ask whether this is true when you have smooth data, and turns out, I mean, just as you can see, like somehow it's no longer true that the function evaluated the loss on the historical data is a unbiased estimator for the loss on the next data point. This is just not true, because somehow I guess I had prettier pictures on my slide, but like roughly what you're allowed to do is like for all times up to t give you some measure that looks like here, and then in the next time step give you a measure here. This is like entirely allowed in this model. So this has like no hope of being true, at least like as stated. Right. So the first, so the historical, it's no longer an unbiased assessment. It has like again no bearing on the right hand side, left hand side, and right hand side. And secondly, you can try to hope to prove things like the second, like an empirical process type bound. But the issue is that data is all dependent. It's extremely dependent data because the choice of measures can somehow, um, yeah, the choice of my points is like extremely dependent. So again, the standard empirical process arguments do not go through, or at least it's not obvious that they go through. Okay, so just to again reiterate exactly what I said before, the main distinguishing factor from stochastic data, and this is the sort of thing that we wanted to capture in this model at all, was that there are distribution shifts in this setup, and because of adaptivity, where the choice of the point at time t can depend entirely on the history, you have no independence. So in particular, you can like the choice of measures can like in so far you see is covered here, but like the orange region is uncovered, and you can get a point from there entirely in the next time step, right? So you can't now hope to have like unbiased estimators of the risk, at least in some nice sense. Any questions about what the challenges here are? Okay, so as I said, you can't hope to have these type of guarantees, at least generically. So, okay, the first technical lemma that somehow allows us to reason about this is something we call the surprise lemma, which is just says that like if you have a smooth sequence of this is just a statement about like again stochastic processes. So if you have a smooth, you can so entirely ignore everything I said about learning if that as this is a statement in probability, I guess. So you have a sequence of smooth measures adaptively chosen even, and then the number of times that the at any given point the likelihood ratio goes above the average likelihood ratio in on the history is upper bounded by some number epsilon t, and epsilon appears in the amount that you deviate from the average. So this is a bit technical, but let me try to again hopefully explain this in pictures. Like I said, like you can have a sequence of like distributions that like don't have any relation to each other, but because these are smooth distributions, they somehow take up some notion of volume of the space, and as you move along, eventually they're forced to have some notion of coverage on each other. So in some amortized sense, somehow history has to somehow be predictive of the future, at least in this sense, as long as you have some non-trivial volume. So that's what's happening. Again, intuitively, the restatement of that thing is that if you have the historical distributions that you've seen, the number of times that you are like much bigger at any given point, much bigger than the history that you have seen is bounded for most, like the number of times that it will happen is small. And for most time steps, you're like the future distribution is somehow covered by the past distribution in again some amortized sense. Does that make sense? So again, you don't have uh, another way of putting this is just that for any given function, the risk of this function compared to the is upper bounded by its risk on the historical data for most time steps t. Here again you have a fresh, these are on evaluated on fresh samples, so this is like population loss. So that's yes. What do you mean? So I mean, I guess that you're saying, again, this is just some balancing. This is maybe think of this version is sort of the better version of thinking of this. Yeah. Does that make sense? Good question. Yeah. So again, the fully formal sort of like technical version of the statement, maybe also answering Alex's question, is that somehow if you balance all the terms, what you get is the, on average, for any given function, the risk on the realized data somehow is controlled by the loss on some independently resampled copies of the data. So again, to be entirely technically clear, you should think of this resampled data in this like adaptive setting as coming from a tangent sequence, because again the distributions depend on the entire history. So you should think of it as condition on the condition on like up to some time t, pick the corresponding measure and then resample from that measure. So such a thing is called a tangent sequence. So that's what this tells you. Okay, so this gives you a way to sort of deal with the first problem that you had, which is that like the data on the history was not an unbiased estimator of the things you saw, but what this tells you is that it sort of is in some amortized sense. So it's not actually true, but it's sort of true in some, again, average sense. That's what that previous lemma told you. So this again lets you get away with this sort of thing. There's still an issue, which is that even if you did have access to even if you had access to controlling this, but this is only evaluated on an independent copy of the independent resampling of the point, not on the actual evaluated point. So somehow the issue that you still need to control is some term like this, where you want to relate the resampled point with the point that you actually saw, like supremum over the whole function class. If you could control it, you can basically do exactly what I did before, and this is just going over the same steps as before, with instead of having a unbiased estimator, having this amortized thing, and you would like get the risk part. But the issue fundamentally is that when can you control such a term of this form for dependent data? So again, the key issue is that x's are all completely dependent on each other. Okay, so again, as before, the challenge is to handle sort of potentially arbitrary dependencies on the points that you xc's that you see. Okay, so the second sort of technical solution to this problem is that you have some notion of like stochastic embedding that happens because of smooth data, which is that for any smooth distribution, what we show is that there is a coupling between the sample from the distribution and independent samples from the distribution mu, such that with high probability you have that the sample xt is in in this data set of independent samples. So this sort of stochastic embedding property is true with high probability. So the high level intuition for why this is useful is that xt is some arbitrary stochastic process, but the zt1 to ztk are like come from independent data. So it's just sort of hopefully easier to handle. So again, intuitively, you have some data that's somewhat arbitrary, but it sits inside somewhat much more structured data. It's just all independent. So any questions about this? Yes. I don't see why not, right? Because they can, these are not independent. These are independent, but these to have some joint distribution amongst them. So that's totally like why not? Like it can have. I mean, I guess maybe it's non-obvious, but like for example, let's say you take two Gaussians, right? And let's say the mu's are like somewhat far apart. They have some finite TV distance, so there is some coupling that will have like some finite probability of them agreeing, right? So again, there's a minimized over coupling somehow. So again, these are not independent. These are independent, and these have some joint distributions. Does that make sense? Yeah. So these are like abstract objects that you're entirely right, but like this is still like But it's actually surprisingly easy to prove. Maybe I can tell you offline. So then you'll believe me. Okay. So any other question? Okay, so why is this useful? The reason why this is useful is that this gives you a sort of like very interesting decoupling inequality. Uh, so typically, again, when you're analyzing like randomized algorithms or like uh, statistical learning algorithms, what you want to do is sort of like bound the probability some bad event happens on the data that you see. So those red triangles are like supposed to be bad, and you want to say bound the probability that like or like count the number of times some bad thing happens. What this sort of like coupling lemma allows you to do is say that okay, with high probability these points are a subset of these larger set of points, and therefore and under this larger set of points are IID if looked by themselves, and then you can bound the error on that those set of points. So that's sort of roughly what's happening. Mathematical formalization is that if you have a bunch of positive functions and you want to evaluate the expected supremum of this bunch of positive functions on a smooth sequence of data, then this is upper bounded by the corresponding empirical supremum on an independently drawn sequence of data, but on a slightly longer sequence. So the sequence length sort of blew up, and you pay for this sort of blow up in the length of sequence in some exponential, like exponentially decaying additive error term. So you prove some decoupling inequality of this form. So again, just to recall, this sort of expected suprema comes from trying to analyze algorithms such as empirical risk minimization, because they have data dependent. You pick data dependent functions as your predictions, and they sort of lead you to this empirical suprema. So that's sort of what's happening at a high level. And so this is what we would call a decoupling inequality. And just again to contrast this with something naive that you can do, which is just like at each time step you have a smooth distribution, so that gives you like a multiplicative 1 over sigma factor in terms of the expectation. So if you repeatedly did that, you'll get an exponential sort of like dependence. So what this inequality is telling you is allowing you to do something that behaves much better, but gives you an additive, pays an additive offset. And in most settings we're interested in, somehow the additive offset is much better than this multiplicative exponential. Right, so again, this blows up the length. Here the length is not blown up, but it pays again this exponential. Okay, any other question? Any question about like why this might be interesting? So again, so once you have this, okay, maybe this is a little technical and this is a little too late in the workshop to sort of make sense, but I'll quickly go over it and happy to talk about it offline. But somehow once you have this coupling inequality, you can try to sort of bound the process that you wanted to bound in terms of like maybe the process evaluated on the slightly longer sequence. It again helps to sort of look at a symmetrized version of the process. This is again, if you've seen symmetrization before, that's just like replacing empirical supremum with the corresponding thing with like Rademacher or like Gaussian random variable there. But you can now try to say that okay, I'll replace these x's with the corresponding z's, and it only has to get larger because it's bigger. But this is actually not a true fact. This is not true that this supremum is larger when you increase the data set size. So if there wasn't this offset term, turns out it's actually true for Rademacher complexity from Jensen's inequality. But like when you have this offset thing, this is it's not true. So somehow to deal with this, we have to do some again technical workarounds, which leads it to be connected to actually somewhat interesting objects in integral geometry and convex geometry. So somehow to deal with this, if you just take by Jensen's inequality, take a log and an x, you get this other stranger looking quantity. And turns out the stranger looking quantity is like a very natural quantity called the Wills functional of the corresponding convex body. Again, if you haven't seen, again, talk to me offline if you're interested. If you haven't seen this before, this is a lot. And so it's exactly the same as the Gaussian complexity, but with this offset term and this log some x. Turns out this is related to the moment generating function of the Gaussian supremum somehow. But yeah, interesting quantity, it behaves really well. And the point that why this is all interesting is that like this is amazing paper by Joao Mutada that somehow analyzes uses this to for the square laws give you the bounds in terms of this Wills function. Furthermore, the key point that the Wills function satisfies is that adding data only sort of increases the Wills function. This is again not true for the other quantity that we were looking at. So somehow it makes us only larger. So with that somehow and putting together everything that I said before, you can upper bound the empirical supremum in terms of the Wills functional, and the Wills function somehow is upper bounded by good quantities such as the Gaussian complexity and VC dimension. Right? Okay, so to recall everything that I said, when you have smooth data, you have this upper bound in terms of the VC dimension and also a corresponding lower bound in terms of the same quantity. So somehow covariates are fundamentally harder to deal with than you have IID data. And at a high level, this was a set of techniques that allowed you to deal with covariate shifts and handle get regret bounds even in this again changing environment. Let's say a high level check. How many minutes do I have? Okay, yeah, that much I got. But yes, okay, so I'll quickly summarize what I guess I had. The high level key takeaways is that smooth data formalized in this way, which is asking for a bound on the likelihood ratios, gives you a way to bridge the efficiency of statistical learning and the robustness of online learning. And we saw two technical tools. One is this the surprise lemma, which tells you the number of times you can be surprised by smooth data. This is some again quantitative ergodicity theorem. Again, talk to me offline if that sentence doesn't make sense but sounds interesting. And some again compactness of the space. And again, just to recall what it told you that the number of most of the time somehow historical data gives you some hint about the future as long as you have like again some quantitative assumption on the data generating process. And secondly, we saw this coupling lemma, which tells you that you can embed like sort of large so again stochastic sequences from this smooth distribution into independent IID a point, and that allowed you to do sort of like allowed you to do this decoupling inequality. And so again to recall the bounds that we saw, we have the bounds on sort of the performance of ERM. You got these rates that depended only on sort of well-behaved quantities as opposed to not being able to learn at all. And you have the corresponding low bounds. And yeah, so this is again the high-level takeaway. So I had a bunch of other stuff about what you can achieve with smooth online learning, but again, like end of the talk, end of the workshop. So I'll just like skip over it. I'm happy to talk about this again offline, but somehow it's also true that like the same setup allows you to get sort of efficient algorithms as well, which were not possible without smoothness. So again, at a high level, you can get both statistical and computational efficiency in some very general setting under this setup that we just mentioned. So it also turns out to be connected to other several other areas because again, as I mentioned before, online learning is a very interesting abstract primitive that's useful in like a lot of algorithm design and has connections to several other areas such as privacy, data-driven algorithm design, sequential decision making in more like abstract settings such as bandits, RL, and robotics, and also like learning in games. And because again how general these results are, you sort of get somewhat black box connections to several other areas which either had like computation or statistical hardness in the corresponding settings. So it's sort of interesting how some simple setup like what we saw before has such wide-ranging applications. Anyway, so again, key takeaways is that smooth data, which is the efficiency of statistical learning and robustness of online learning. And we saw two technical tools. One was this like compactness argument, which is the surprise lemma, and this coupling lemma, which again is closely related to approximate notions of rejection sampling. Again, the broader questions that I'm interested in, at least, is at some philosophical level, how should we think about the relationship between the past data that we have collected and future data that you want to make predictions on in the setting of learning? And in at least in this broad setup, what is again the algorithmic question? How should we pick our predictors, and what computation should we be running? And again, in this sort of broad abstract setting, what data and how much data should you collect, and what makes a prediction problem hard? This is the abstract question I'm interested in, and happy to again chat about any of this. Again, thank you, and I'm happy to take any more questions.
All right, so there were quite a few questions. Are there any remaining?
I mean, regarding other connected work, do you want to spend 2 words on the private setting?
Oh yeah, so roughly the privacy. Okay, so privacy and online learning turn out to be like very closely related. I don't know if you know this equivalence of online learning and statistical, private packed learning work that was there a few years ago. Okay, it doesn't matter. So it turns out those were like whenever you can do private packed learning, you can do online learning and vice versa. So somehow classes that are not online learnable are also not privately learnable. That's like this high level correspondence. So you could ask whether there is like, now that because you can do online learning in this setup, does that give you some interesting setting where you can do private learning? That's the natural question. And turns out, yes, you can. And that sort of smooth analysis is sort of morally equivalent to learning with like public data, where you have some private data and you also have some unlabeled public data in the side, and you want to sort of learn in this setting. And there's like a 1:1 correspondence between, roughly a 1:1 correspondence between this setting and that setting. So you can actually like now learn classes that you would not have otherwise been able to learn. So like I said, that's somehow the kind, yeah. But thanks for the question.
Any other? Yeah.
I was wondering if you could just give the flavor of the lower bound. Like, I assume it's some sort of thing where you're chasing measures that are moving around.
Exactly. Yeah. That's a good way of thinking about it. So it's okay. I'll give you a simple lower bound, and then maybe we can talk offline about with the more general lower bound. But like the simple lower bound is super simple. Let's say you're doing linear classification, and you're like, let's say you pick the half space that's like leftmost on like the, you know what I mean, right? Okay. So and then you can have measures that sort of like keep moving. Once you make enough mistakes, somehow keep moving by a little bit, like epsilon over square root, sigma over square root t or so. Again, you need to balance these terms, but like, and that's where the lower bound comes from. So they keep moving. There's like, you have enough coverage because of which you can. There's a lot of time for me to move till I hit the end, but there's enough again gap between what you have seen already and what now you haven't seen, that you make a mistake sort of sufficiently often. So balancing these two will get you that low. But basically the surprise lemma is tight. That's sort of what's happening. But this doesn't rule out all algorithms. This only rules out like this like silly ERM that I told you. But like ruling out all algorithms needs some technical thing about little stone trees and so on. But that's okay. Yeah. But yeah, that's what's happening roughly.
Any last comment? So if there's not, we can thank Abhishek again, please.